Okay, today we'll cover part 4 of 18.2, and we'll start this lesson off with example 6. So example 6 can be found in your textbook on page 155. So I will just give you some time to read it. Okay, you can pause the video, okay, read it from your textbook. If not, let's begin. So now, a particle P moves along a horizontal straight line, so at t seconds after motion has begun, its displacement is given by this equation over here. Find the expression for the acceleration in terms of t. Quite simple, okay. Basically what we are saying here is, if you differentiate displacement with respect to time, what you get is the velocity. So in this case, what you have here is 3t squared plus 14t minus 2. This one quite simple, all right? Okay, but let me just copy that down. 3t squared plus 14t minus 2. Okay, I think I missed out a t here. Okay, now I move on to part 2 itself. For part 2 itself, a second particle Q starts its motion at the same time as P and moves down the same horizontal line as P. Its acceleration, okay, t seconds after motion has begun, is given by 6t plus 4. Given that it has a velocity of 2 meters per second when t equals to 1 and an initial displacement of negative 1 meters, obtain expressions for velocity and displacement. Okay, now, so from acceleration, if you remember, to get back to velocity, so what I need to do is to integrate 6t plus 4 with respect to t. So in this case, what I get is 6t squared over 2 plus 4t. Don't forget our integration constant, our friend c. Okay, let me call him c1. So velocity of q is given by 3t squared plus 4t plus c1. Now, to solve for c1, we know that there's a velocity of 2 meters per second when t equals to 1. So velocity of 2 meters per second, t is equals to 1. And if you very quickly solve that, your constant c subscript 1 is equals to negative 5. Hence, I've already got the first part, whereby the velocity of q is given by 3t squared plus 4t minus 5. Now, if I want to get the displacement of q, what I need to do is to get the displacement of q, what I need to do is to integrate the velocity with respect to time. And the velocity is given by 3t squared plus 4t minus 5 with respect to time. In case you're wondering where I got this is simply from what we have solved in the earlier part. So if I start to integrate, then I have another integration constant, c2. Now, in order for us to solve for c2, notice that the initial displacement of negative 1 meters. What does that mean? So initial displacement, initial means that t equals to 0, but however, they actually tell us that initially there's a displacement of negative 1. So what I can say is negative 1 is equals to t cubed plus 2t squared minus 5t plus c2. Okay, then not forgetting that actually, okay, all the t is actually 0. So here is 0, 0, and 0. So it's 0 cubed, 0 squared, then 5 times 0 plus c2. If you solve, what you'll find is that c2 is equals to negative 1. Hence, the displacement of particle q is equals to t cubed plus 2t squared minus 5t minus 1. So I already have my expression for the velocity of q. I have my the displacement of q given by these two equations over here. Okay. Now, part 3. In part 3, what they want us to do is to find the value of t at the instant when p and q collide. Okay, what do they mean by they collide? So in order for something to collide, okay, let me just give you a simple analogy. Okay, if friend A is in school and friend B is at Hougang Mall. Okay, they are at different places. Is it possible for them to collide? Cannot be, because one's in school, one person is in Hougang Mall. They cannot possibly bump into each other. They cannot collide with each other. So the only possible way to collide with each other is to be at the same place at the same time. So collision means to be at the same place at the same time. So in terms of kinematics, basically what I'm saying is that the displacement of P is equal to the displacement of Q. So when they are at the same displacement, they're at the same place at the same time, then they will collide with each other. So if you go and flip back to what we have initially, okay, for the displacement of P, what we saw from the earlier part is such that t cubed plus 7t squared minus 2t minus 3 is equals to t cubed plus 2t squared minus 5t minus 1. So if you simplify everything, what you get is 5t squared plus 3t minus 2 equals to 0. Quick factorization produces 5t minus 2, t plus 1 equals to 0. So t equals to 2/5 or t equals to -1, which you have to reject. Why you reject? Because you cannot go backwards in time, so time must be positive. So t equals to 2/5. Hence, what I'm saying here is that when they collide, the time is equals to 2/5 second. Okay, part 4. Are P and Q moving the same direction when they collide? Okay, one way to measure direction is to see the velocity of the object, so or the particle. If they have the same symbol, okay, it means they're moving with in the same direction. If the velocity is of a different symbol, one is positive, so if it's positive, it means that it's moving towards the right. When it's negative, it means it's moving towards the left. If you define the right as positive, so what we can do is to see their velocity. So what I can do is when t equals to 2/5. So initially we have the velocity of P. So the velocity of P, which we found earlier, is 3t squared plus 14t minus 2. What we'll do here is when I sub t equals to 2/5, so I get 2/5 squared 14 and 2/5 minus 2, the velocity of P equals to 4.08. So what does 4.08 mean? 4.08 means that if you define right as positive, P is moving towards the right, okay, at time equals to 2/5. Similarly, I apply this same concept to Q. So velocity of Q, if you remember from the previous part, what I had is 3t squared plus 4t minus 5. So when my t value is 2/5, I just substitute in the values here, and the velocity of Q in this case is -2.92. Hence, if you notice positive, this particle P at that moment in time is moving to the right, while this symbol here is negative, which will imply that Q is moving towards the left. So therefore, one is moving the right, one is moving the left. Okay, hence, okay, the particles are not moving in the same direction. In the same direction. Okay, that's it for example 6. Now I urge you to pause the video, okay, read the question and try 6. This can also be found in your textbook on page 156. Okay, now for the first part, the velocity of each particle in terms of t. So in this case, what we have, alright, is there is quite a lot of information here. So now what I can start with, right, is that, right, for P, they tell us that P moves with a constant acceleration of 1 meter per second square. So therefore, the acceleration of P is given by this 1 meters per second square. If I integrate, okay, to get my velocity, I get 1. Okay, I integrate 1 with respect to time, get t plus c1. Then I learn that when my at initial velocity, when my initial time, the velocity is 7. So because p starts with a velocity of 7 meters per second, hence, okay, if I solve that, I will say that since my velocity of p is t plus c1, so when my velocity is 7, the t is 0 plus c1. Hence, I have found that c1 is equals to 7. So the velocity of p is t plus 7. Now, for q itself, they actually give you this equation here. And it says that it starts from rest and moves with acceleration of a. So it means that at rest, okay, so initially when my velocity is 0, my t is equals to 0, or rather starts from rest means when t is 0, my velocity is equals to 0. Now if I start, okay, to integrate the velocity of q, what I'll get is 250 plus 3 over 10 t squared plus c2. So as I explained earlier, when t equals to 0, the velocity of q is equals to 0. So if you solve all of that, 0, 0, c2 will give you the value of 0. Hence the velocity of q is 250 plus 3 over 10 t squared. Now next is this, the distance traveled by each particle in terms of t. So now if I want to find distance, actually I'm trying to find the displacement, I have to integrate. So once again, you have this for particle p, you integrate, you get half t squared plus 7t plus c3, another constant. Then for particle p, we know that the displacement is 0 when my t is 0. These are the initial conditions. I find that c3 equals to 0. Then the displacement of p is given by this equation. Same idea for q. Initially from part 1, we have this, which is the velocity of q. If you integrate with respect to time, you get this. Now, when t equals to 0, my displacement equals to 0. They both start at the starting point, so c4 is 0. If you have done all of that correctly, what you get is displacement is 1 over 10 t cubed plus 1 over 5 t squared. Now, the distance when p and q collide, remember the Hougang Mall and school analogy. So in order for them to be colliding, they need to be at the same place, so the displacement is equal. We equate the two displacements that we got from part 2 together. Then we just simplify the equation, and then you factorize. You get two values. T is 10, t is 0, and t equals to negative 7. So t equals to 0, okay, we will reject this because t is greater than 0. So they collide later. So at the start, right, they just start there, but they don't count it as colliding. So therefore, the first time that they will collide will actually be equals to t equals to 10. So therefore, when t equals to 10, what we have is the distance is 120 meters itself. Finally, in part 4, when t equals to 10, alright, the speed of each article, if you just substitute into the velocity of p, velocity of q, okay, you'll find that the speed of each particle when they collide is 34 and 17 meters per second respectively. This one is 17, this one is 34. And this concludes part 4 of 18.2.